Robot metabolism, self-repairing robots that grow by eating other robots. Imagine a future where robots are not only smart, but also capable of evolving and healing themselves, a notion that some find both fascinating and alarming. Engineers at Columbia University are pioneering a radical step forward by developing robots that can grow, self-repair, and even change their shapes by absorbing parts from other robots. This breakthrough, which brings us a little closer to what many refer to as the singularity, involves units known as Truss Link. These are modular, bar-like components with magnetic ends, reminiscent of geomag building toys, that can extend, contract, roll, and connect with one another seamlessly. While these aren't yet complex autonomous soldiers running massive assembly lines, they do represent a significant leap towards robots that can sustain themselves physically in addition to processing information autonomously. The lead researcher, Philippe Martin-Wider, emphasizes that real autonomy in robotics isn't just about artificial intelligence. It also requires the ability to physically maintain and repair one's own systems. He draws an analogy to biological organisms that absorb resources and recycle parts, highlighting that these robots can grow, adapt, and fix themselves using materials available in their environment or directly from fellow machines. In an eye-opening demonstration, the research team showcased this self-sustaining ability as the stick-like robots transitioned from flat, two-dimensional structures into fully three-dimensional forms through cooperative maneuvers. As one example, a robot used an extra module as a makeshift walking cane, which impressively increased its speed on a downhill slope by more than 66%. But here's where it gets controversial. When one group of robots actively assisted another in transforming its shape or jettisoned a malfunctioning unit in favor of a viable one, it raised profound questions about where we draw the line between assistive behavior and autonomous self-replication. Co-author Hod Lipson further explains the urgency of this innovation. Although advances in machine learning have propelled robot intellect far ahead, their physical design remains static and lacking in adaptability. In contrast, biological entities excel at modification and self-repair. This discrepancy underpins the vision that, one day, robots must be able to recycle their own parts, much as organisms reuse amino acids. This inspiring drive has even led researchers to formalize their own set of guidelines for what might be dubbed robot metabolism. The first rule insists that any robotic growth must be powered solely by its own mechanisms, utilizing only parts from identical robots as external support. The second rule limits external inputs to strictly energy and physical materials, forbidding any novel components from being introduced. Potential applications for these modular, shape-shifting robots are vast and exciting. They could play crucial roles in disaster recovery scenarios, where adapting to unpredictable environments is critical, or in the challenging realm of space exploration, where self-sufficiency is a boon. While we have seen other shape-shifting robots before, like the GoatBot, ATMO bot, and even Virginia Tech's innovative model that transitions metal from liquid to solid, the Columbia prototypes stand out. They represent a unique form of self-assembling, self-repairing technology that pushes the envelope further than earlier models, such as MIT SimBlocks. And this is the part most people might miss. Despite some eerie science fiction overtones reminiscent of self-replicating machines, the researchers argue that these developments are not cause for alarm, but a necessary evolution. Ho Lipson himself reassures skeptics by noting that as our reliance on robotics in everyday life grows, from driverless cars and automated factories to missions in harsh environments, we must eventually let robots take care of themselves. But does this self-sufficiency signal the dawn of a future where machines might evolve beyond our control? What do you think about the idea of robots that can essentially eat other robots to better themselves? Share your thoughts and join the debate. Self-healing robots, the future of autonomous repair. Imagine a world where robots can heal themselves, adapt to new situations, and even grow new parts without any human intervention. Sounds like science fiction, right? But what if I told you that researchers at Columbia University have already made significant strides in making this a reality? Welcome to the fascinating world of robot metabolism, where machines can physically sustain themselves, just like living organisms. We've all seen robots do some incredible things, from performing complex tasks to exploring space. However, their physical structures often limit their movement and capabilities. Traditional robots are rigid and rely heavily on humans for maintenance, repairs, and upgrades. But what if robots could break free from these limitations and become truly autonomous? This is exactly what the researchers at Columbia University have been working on. They've developed a concept called robot metabolism, which enables robots to physically grow, heal, and improve themselves. This new technology mimics the fundamental biological principle of adaptation, where living organisms absorb, integrate, and repair themselves. In the case of robots, this means they can absorb and reuse parts from their environment or other robots, eliminating the need for human intervention. But here's where it gets really interesting. The researchers have demonstrated this concept using something called truss links, simple magnetic sticks that can expand, contract, and snap together at various angles to form complex structures. These truss links can enable two-dimensional shapes to self-assemble and transform into 3D robots, which can then integrate new parts to boost their capabilities. For example, a tetrahedron robot that grew a walking stick was able to zip downhill 66.5% faster. The potential applications of this technology are vast and varied. Imagine robots that can independently maintain themselves, grow, and adapt to new situations in disaster recovery or space exploration. These robots could repair themselves on the fly, build and adapt without human resupply, and even develop physically and endure in extreme environments. Of course, this raises some interesting questions. What does it mean for a robot to be truly autonomous? Can we trust robots to make their own decisions and adapt to new situations without human oversight? And what are the potential risks and consequences of creating robots that can physically sustain themselves? As Philippe Martin-Wider, lead author and researcher at Columbia Engineering and the University of Washington, notes, true autonomy means robots must not only think for themselves, but also physically sustain. DARPA-funded robot metabolism, robots that heal, grow, and evolve by consuming others. Imagine a world where robots can not only think for themselves, but also sustain and enhance their own physical forms. This intriguing concept, funded by the Defense Advanced Research Projects Agency, DARPA, has been brought to life by engineers at Columbia University through a groundbreaking process they call robot metabolism. This innovative technology allows robots to consume other robots, utilizing their components to heal, grow, and evolve. The researchers assert that for robots to truly achieve autonomy, they must be capable of maintaining and improving their physical capabilities. As artificial intelligence systems continue to advance their autonomous functions, this development is seen as a crucial step towards creating self-sustaining robot ecologies. Philippe Martin-Wider, a lead researcher from Columbia Engineering and the University of Washington, emphasizes that just like living organisms absorb and integrate resources, these robots can grow, adapt, and repair themselves using materials from their surroundings or from other robots. Currently, robots are limited in their ability to change or repair themselves without external help. The Columbia team points out that this lack of autonomy has left modern robots feeling stuck, as they are typically designed as closed systems that cannot grow, self-repair, or adapt to their environments. This issue is compounded by the rapid advancements in robot intelligence, which have outpaced their physical capabilities. Hod Lipson, a professor of innovation at Columbia University and co-author of the study, notes that while robot intelligence has made significant strides through machine learning, their physical forms remain rigid, unadaptive, and unrecyclable. In contrast, biological organisms thrive on adaptability, capable of growth, healing, and environmental adjustment. Lipson argues that just as modular biological systems can reuse components like amino acids, robots should be endowed with similar capabilities, which he refers to as a nascent form of machine metabolism. With the support of DARPA and the National Science Foundation, NSF, Wider and his team have initiated a transformative approach, beginning with a robotic device known as a Truss Link. Drawing inspiration from the Geomag toy, the Truss Link is described as a simple, bar-shaped module equipped with flexible magnetic connectors that can expand, contract, and connect with other modules at various angles. This adaptability allows the Truss Link to create increasingly complex structures. In a series of laboratory tests, the researchers demonstrated that these links could self-assemble into two-dimensional shapes, which could then morph into three-dimensional, functional robots. In the next phase of their research, the robots showcased their metabolism by enhancing their abilities through the integration of new components. For instance, one of the tetrahedron-shaped robots incorporated an additional link to serve as a walking stick, resulting in a remarkable 66.5% increase in its downhill speed. While the idea of robots that can adapt, improve, and potentially self-reproduce may evoke unsettling sci-fi scenarios, Lipson argues that as we increasingly rely on robots in our daily lives, ranging from driverless cars to automated manufacturing, the impracticality of keeping them dependent on human maintenance becomes evident. As we delegate more responsibilities to robots, who will maintain them? Lipson questions. We cannot expect humans to handle all maintenance tasks. Ultimately, robots must learn to care for themselves. The study concludes with a call for further research to explore the potential applications of robot metabolism. The team envisions a future where robotic systems, from autonomous vehicles to spacecraft, exist within robot ecologies capable of self-maintenance. This could enable them to grow and adapt to unforeseen challenges, much like biological organisms do. By mimicking nature's strategy of constructing complex structures from simple components, robot metabolism could lead to autonomous robots that are physically resilient and capable of development over time. Weider believes that this advancement will bridge the gap between artificial intelligence and the physical realm, allowing robots to not only think, but also adapt and grow, thus creating a new level of autonomy. This self-sufficiency could revolutionize various industries, making robot metabolism as ubiquitous as the intelligent AI we use today. Initially, these systems may find applications in specialized fields such as disaster recovery or space exploration. Ultimately, the potential exists for a future where AI can construct physical structures or robots, just as it currently composes and organizes text in our emails. The research titled Robot Metabolism: Towards Machines That Can Grow by Consuming Other Machines was published in Science Advances, with funding from DARPA and the NSF AI Institute in Dynamic Systems. Christopher Plain, a science fiction and fantasy novelist, serves as the head science writer at The Debrief. You can connect with him on X, explore his literary works at plainfiction.com, or reach out via email at christopher@thebrief.org.